Hello again. In this video, we will talk about illustrating epidemiological concepts with the SIR model. Now, if you remember last time, we constructed a simple SIR model using an Excel spreadsheet. First concept that we will illustrate is flattening the curve. Now, earlier on during my series of videos, I compared the COVID cases for New York City with the COVID cases for Texas. And we saw that the New York City had a very sharp peak of cases around April. In Texas, the peak is much more flattened out. Now, if you compare the death rate in New York was more than 3 times the death rate in Texas. And part of the reason is that the number of deaths was limited, the number of case infections was limited so that the hospitals could manage them. Here there were too many infections for the hospitals, so many people died. And people were not prepared. So we can illustrate flattening the curve using our simple Excel model. Okay, so here I have a completed SIR model. I am sorry the colors are not consistent with my slides. I've changed S to blue, I to red, R to gray. All right, so in my slide here, I was using S as yellow, I as red, R as blue, but now I've changed the colors. So S is blue, I is red, and R is gray. Here we have our SIR model with some parameters, and here you can see a very sharp peak. Now in this model, my contacts per day is 12. That's a very high contact rate. Now suppose I introduce social distancing so that my contacts per day reduces to 6. See how the peak has flattened out. Right. Now suppose I also ask people to wear masks. People wearing masks will reduce the transmission rate. Let's suppose that reduces the transmission rate in half. You can see the peak is flattened out even further. In fact, there's no peak at all. But if I increase this back to 0.04, then you'll see that there's a very, very flat peak. Right. So this is an illustration of peak flattening through control of the parameters, through distancing and masks. Here, just by reducing the contacts from 12 to 8, my peak is very much flatter. Okay. I'm sorry, the color here is green, it should be gray, but you can see that the peak is flatter and the number of people who get the disease is reduced by 200,000. Right, so that's your peak flattening. All right, now let's go on and talk about herd immunity. Here you have the curve of recovered patients. This curve is flattening. This curve continues to rise. Now, why is the curve flattening there? Let's explore this phenomenon. Now, in this model, I've chosen a case where there are 8 contacts per day, and I start with 0.1% infected. So you see I still have a very sharp peak. Now let's see what happens if, and one more thing, you can see that 90% of people become infected and recover. So this is a very bad scenario. Let's see what happens if I increase the number of recovered at the beginning. Let's take the number of recovered up to 20. All right. So we start out to 20. Now here you can see that only 80% of the people eventually became infected and recovered. I still have a sharp peak, but let's increase the recovered more. Let's increase it to 40. It's down to 70%. Let's increase it still more to 50. A little more, let's make it up to 60. Right. Now what's happening here? Notice that here the infected are decreasing. Let me zoom in so you can see that better. The infected numbers here are decreasing. Okay. There are so many recovered in the population that new infections do not happen very quickly. Why is that? Because many of these contacts are with recovered and not infected. Okay? So if I start out at 60% recovered, then you can see that no more infections will take place, or very few additional infections will take place, and the disease becomes stable. Now compare this again with my original case where I started out with 0% recovered, and in this case I have 900,000 people become infected. Here if I started out with 60% recovered, then I have no more infected. Okay. So once you reach the point where a large proportion of your population is recovered and immune, then your population becomes stable. I should also say at this point that another strategy you can use is to do testing. Now what testing will do is it will reduce the infectious duration, because if you test someone and you find that they're positive, then you will keep them separate from other people, and that will reduce the effective infectious population. So if I reduce this to 2, say, and let's take this back up to 0, you can see that this also greatly reduces the infection. Right? Originally here I had 5, and if I reduce the infectious duration even to 4, you can see how the peak is flattening. All right. So just to summarize this point, here if I have 0% at time 0, I do get more infected. But if I have a high level of immunity at the start, then I do not get many additional infections, and the population is stable. In this case, eventually 60% of the population became infected and recovered. Here, if I started at 400,000, I remain at 400,000. Okay. So this is why you want to flatten the curve, because if you flatten the curve, then you do not get these high amounts of infected and recovered. You reach this level gradually, and you have no more infected. All right, so that explains herd immunity. All right, let me talk now about the basic and effective reproduction numbers. This is a very important concept in epidemiology, and it's one of the keys to epidemic control. The basic reproduction number, we use R0 to be the symbol for a basic reproduction number. The basic reproduction number is defined as the average number of additional infections produced by a single infection, assuming that everyone is susceptible. So we have a large population of susceptibles and one infected person. We want to know how many additional infected people that one infectious person will produce. Okay, so here's an example. I have an index case, which is a single infection, and this infection produced 3 secondary infections directly. So we call this generation 1. Now these 3 people infected more people. This infectious person infected 2. This infectious person infected 3. This infectious person infected 1. All right. So you can see that, of course, not everybody infects the same number of people. But we can see on the average, each person infected 2 other people. So that's generation 2. In generation 3, we have a different situation. This person infected 2, this one infected 3, this one infected none, This one infected 3, this one infected none, this one infected 4. So you can see there is a variation. But we can take an average. One index case has produced 12 third-generation cases. So after 3 generations, one case has produced 12. So on average, if we take the cube root of 12, we get about 2.2. So for each generation, the number of cases has multiplied by 2.2 on average. So from this data, we conclude that the reproduction number is approximately 2.2. Now this is the basic reproduction number. The effective reproduction number is the number of average infections produced by a single infection in the current mixed population. We just saw that you have herd immunity when you have many recovered individuals in the population. Okay. That means that the reproduction number is less because the contacts of susceptibles with the population, part of that is contacts with the immune people. So the contacts that produce infection are reduced, and we have a reduced number of reproduction. So I'll just say that when all the people in the population are susceptible, then the effective reproduction number is equal to the basic reproduction number. Typically, when you start out, there are very few infected, so the reproduction number is equal to the basic reproduction number. As the infection spreads, the effective reproduction number will go down. Okay, so I'll go to reproduction number down here. And here I have a case, 8 contacts per day, mean infectious duration is 5. And you can see that the infection is growing like this. Now let's see if I can reduce the effective reproduction number. In this case, it's clear that the basic reproduction number is bigger than 1, because when I start off, I'm getting more and more infections. Let's see if I can reduce the basic reproduction number. I can do some control measures. I can do distancing and reduce contacts per day to 4. I can do testing, and I can reduce the infectious duration to 3. All right, now look what's happening here. If you look at these infectious numbers here, if I zoom in, you can see that these numbers are decreasing. What's happened? My reproduction number has gone below 1. The infection is controlled, very few additional infections, and almost no one gets the disease. Okay, so this shows how your controls can affect the reproduction number. As long as I can get the basic reproduction number below 1, the infection will die out. If I already have some recovered here, then you can see I can increase my contacts per day. I still have reproduction number below 1. I can reduce my testing. I still have reproduction number below 1. Okay. So after the disease has gone for some time, I still can reduce my effective reproduction number to be below 1 by contacts and distancing. Let's see if I change this to 8. If I change this to 8, you see the reproduction number is not below 1. We still get some additional peak here. So 8 is too much. Maybe I can change to 7. Okay. All right. In this case, yes, my reproduction number is less than 1. These numbers are decreasing. So this illustrates the concept of reproduction number. There's no peak here when the reproduction number goes below 1. I reduced my contacts, so I reduced my basic reproduction number. All right, let's move on to the next, and we'll talk about endemic equilibrium. So far, we've said that recovered individuals are immune to becoming infected. For some diseases, recovered persons are not immune, or immunity is temporary. That means I need to add another transition here, from recovered back to susceptible. So here I have my infection rate, here I have my recovery rate. Now here I have my reversion rate. Now the reversion rate is similar to the recovery rate. I revert to susceptible. The reversion rate is 1 over the mean immunity period. You may remember that the recovery rate was 1 over the mean infectious period. So I need to add this arrow to my spreadsheet. All right, so let's see what happens if I modify my model to include the recovery rate. All right, now I have changed this model to include recovery rate. Here we have reversion parameters. So here's my mean immunity duration. Here I put in a very large number. I put in 1,0,0,0,0,0, so something very large. Now the reversion rate is just going to be 1 over this value. Okay, so here I'm going to put equals 1 over this here. And the reversion rate I've called rho. You can see the value is rho. And I've included rho in my model. If you look here, I've added this term minus rho times G3. That means that the number of recovered individuals is reduced by the reversion rate times the previous number of recovered. I've also changed this formula here to add those recovered individuals who become susceptible. Now in this case, almost no one reverts. So you can see that this is just like we've had before. We have the infection, it goes up, it goes down, and some people become recovered, but eventually no more are infected. We've reached a steady state or equilibrium. Now, what happens when I have a reversion rate? Let's suppose that my mean immunity duration is 100. Let's see what happens over here. Okay, don't see much happening so far. Whoops, that's too much. Okay, let's see, I make my mean immunity duration be 5. All right, now look what's happened. The infected goes up. Let's make it a little bit less so that we can see the difference here. We can make this to be 7. Okay. My infected goes up and it remains. Why is that? Because recovered becomes susceptible again and they can become reinfected. So I do not get the case like I did before, where I have eventually everyone gets the disease and the disease goes to 0. In this case, there is a constant disease level. This is called an endemic equilibrium. So endemic means that the disease always remains and does not change. You can see, for example, there are endemic diseases in Africa. This one is trachoma, and this shows the countries in which trachoma is endemic. Now, endemic is related to the reproduction number. If the reproduction number is greater than 1, then you will always get cases causing new cases, and you will not be able to eliminate the disease. So if R0 greater than 1, disease is endemic and cannot be eliminated. The level of endemic disease is called the endemic equilibrium. If R0 is less than 1, then the disease will die out. If there's no disease, this is called the disease-free equilibrium. Equilibrium means it's a state which does not change. So if my reproduction number is less than 1, I can start with no disease. If someone becomes diseased by accident, maybe someone from another country, if that person comes in, if the reproduction number is less than 1, they will not produce a multiplicity of additional cases. The disease will die out and the disease-free equilibrium is stable. The reproduction number can be reduced by different control measures like hygiene, environmental control, vaccination, quarantine, and so on. The ultimate goal of disease control is to reduce the basic reproduction number to a level below 1. So you can see that in Sudan, it looks like the reproduction number for trachoma is less than 1. So this disease is not endemic, but in other countries like Nigeria, the disease is still endemic. The reproduction number is above 1. So in the next presentation, I will talk about enhancements to the SIR model.